Hi, I'm Micah Woods, Chief Scientist at the Asian Turfgrass Center. I gave a presentation at the Golf Matters New Zealand conference in Christchurch with the title of MLSN, a modern method for turfgrass nutrition. I want to share those slides with you and record this screencast to review what I talked about for people who are interested who didn't have a chance to attend. If you look at this image, we could start in the top right corner and move around it clockwise. I'd given a previous presentation the day before called Beyond the Textbook, where I used that slide with all those images from places that I've traveled to in the past 6 years around the world. I'll put a link to that presentation right up here so you can watch that one if you're interested. So the problem that we have that I described goes, how can we use textbook information to manage all different kinds of turf growing in different types of soils and different climates around the world, and in all those sites we need to produce a different kind of turf, a different type of playing surface, or a different type of visual lawn type surface. There are so many different requirements that it becomes difficult to know what to do with turfgrass nutrition. MLSN is a way to provide the quantity of nutrients to supply based on soil test results for any of those locations in the world and for any of those grass types and for any of those use cases. And it does that by preventing nutrient deficiencies. The grass that's growing in those tubes is all Pen A1 creeping bent grass that was grown from seed. The one at far right is growing in laboratory grade silicon dioxide, quartz, 99.99% silicon dioxide, and it germinated from seed and then it died because it didn't have enough potassium. All of those soils going from right to left have increasing levels of potassium, and the grass that grew from seed has a completely different type of performance. And then the slide at top left is from Habu Country Club, the 9th green on the 1st of July 2001, which was a very hot summer east of Tokyo, where I happened to be the golf course superintendent there that summer. That's Pencross creeping bentgrass on those greens. And I'm pretty sure that if I would have taken a soil sample from those greens and sent it to a soil testing laboratory, I would get back a result with some recommendation or some interpretation that says some elements are quite low and they would need to be added as fertilizer. And you've probably seen this before when you get your results back from a soil test. You'll often see that some elements are classified as low or very low, and fertilizer gets recommended. But sometimes you also have the case, as you can see in that image, where the grass is fine. In fact, the grass is more than fine. It's very good. There is not a blemish on the green. So the question is, if this would test low in phosphorus, for example, is it really low in phosphorus, or is that a misinterpretation? And I can't tell you how many people from around the world have asked me some variation of this question. For example, I've got a soccer field, I've got a football field, and the grass is fine, but it tests extremely low in phosphorus, and phosphorus keeps getting recommended, but the grass is fine. And then some people don't apply that phosphorus, and the grass continues to be fine. And then the next year they test again, and they know they haven't applied phosphorus, but they test again and get that test result back, and it again says your phosphorus is low. And people distrust then the recommendations because there is a flaw with soil test interpretation. For anybody who doesn't know, MLSN is an acronym for Minimum Levels for Sustainable Nutrition. That's where the MLSN comes from. This is a modern method for using soil test results to make nutrient, or specifically fertilizer recommendations for turfgrass. But I think that it makes sense to explain some of the context here and to start by explaining why conventional methods aren't modern and then I'll try to explain why MLSN is modern. Remember, in the title of the talk, it is MLSN, a modern method for turfgrass nutrition. And the next two things that I'm going to talk about are how to use MLSN and why MLSN works. And there's a bit of overlap between those because the how you use MLSN is related to why it works, and why it works is also related to how you use it. But I divide that into two sections and give myself a chance to explain it one way and then try to explain it another way. Because it turns out that the conventional methods are the way that a lot of people have been taught and the way that a lot of seminars and textbooks continue to present this topic. And because of that, sometimes the way that MLSN works isn't immediately apparent to people who have not used it before. Let's discuss for a moment why conventional methods are not modern. And I'm talking about methods for interpreting soil tests for turfgrass in order to make fertilizer recommendations. This is an important topic, the topic of fertilizer. I use a quote from 51 years ago, the textbook by, I believe it was John Madison. The book is called Principles of Turfgrass Culture, and he wrote that fertilizer is the #1 management tool. It is worth all the attention you can give it. I love that quote because I like fertilizer, so I'm happy to use that and say, okay, this famous author who wrote a classic textbook half a century ago says fertilizer is the #1 management tool. Actually, if you ask me, I'm going to say it's mowing, okay? Cutting the grass. I think cutting the grass is the #1 thing to get right. But after that, then we do the fertilizer. Anyway, fertilizer is important. We can all agree that for the duration of this talk, let's consider fertilizer as the #1 management tool, and let's give it all the attention that we can give it for the duration of this talk. So in that same decade, 44 years ago, there's a classic article. There's a classic article or a research project by Tom Turner and Donald Waddington. Turner and Waddington in 1978 published an article called the Survey of Soil Testing Programs for Turfgrass. They introduced the topic by saying that they conducted a study to determine differences among soil testing laboratories and fertilizer recommendations for turfgrass maintenance and establishment. And they did this by taking a soil sample, dividing it before they sent it to the laboratories. They took one big soil sample and they divided it into sub samples, and then they sent each one of those ostensibly identical samples to different laboratories, and they wanted to see how the results came back. Well, the results came back really different. Like, okay, not only did the labs use different methods, but really they interpreted the results completely differently, to where the recommendations were 3 or 4 times different, 300 or 400% different, depending on what laboratory was making the recommendation. And they wrote something pretty revelatory in that article. In that same article, in the introduction, as they did a review of this, they found 3 particular items that I think are pretty damning in how much trust we could have in the recommendations in 1978. So they said that turfgrass recommendations, and by that they mean turfgrass fertilizer recommendations that are based on soil tests, they are based on research done with other crops. They are based on turfgrass fertility studies that were not designed to relate to soil testing. And they're also based on the best judgment of the agronomist making the recommendations. So that is a bit of a problem. They identified that in 1978. Okay? So this is historical. This is the conventional way of doing soil testing. And if we look in 1978, that was the situation. And we might think that after 23 years, so that goes up to 21 years ago, perhaps some of those issues had been corrected. But this quote from the Turfgrass Soil Fertility and Chemical Problems book by Doctors Caro, Don Waddington again, who was also a co-author of that 1978 article, and Dr. Paul Reiki were the co-authors of this book. They put a very interesting comment in there. On page 164, they wrote that in some cases, turf grasses have been placed in a high P and K requirement category. This decision was based on economics, not agronomics. The cost of fertilization was not considered of primary importance for turf. What that means is they don't have any data to show that turf needs to be high in P or K, but it was assumed that there could be an economic response to P or K for agricultural crops. And for turf grass, the economics didn't really matter because we assume we always want high quality. So since they don't have any data, the people making the recommendations would just automatically classify it into having a high requirement. Now, this also coincides with trying to have a high nutrient level in the soil, classifying turf as requiring a high P and K requirement from the soil. This coincides at the same time with more and more sand top dressing, which means the soils are inherently going to be able to hold less P and K. There's all kinds of things going on that just don't make any sense with the traditional way that things have been done. So this problem still persisted in 2001, and I am sorry to tell you that that problem has persisted. 9 years ago, there was a review article by Beth Gertall and Kevin Frank, and they wrote about phosphorus and potassium in a review article, Potassium and Phosphorus Research in Turfgrass. This was published in 2013. On the topic of phosphorus, they say the calibration of soil P with turfgrass growth and subsequent P fertilization recommendations is scant and additional data is needed. Many current recommendations for P fertilizer for turf grasses are based on forage or field crop calibration data. Okay? So that same problem that was identified in 1978 by Turner and Waddington, it persists in 2013. And on the topic of potassium, from that same article, Kevin and Beth wrote, relationships between extracted soil potassium fertilization rates, and turfgrass response needs additional study. Such work is especially missing for the sand-based systems in which many turfgrasses are managed. So that is my little historical tour of why the status quo, the conventional guidelines, the conventional way of interpreting soil tests for turfgrass, it's not modern. We have the same problems that we had in the 1970s, the same problems that we had in the 1960s. I think we can consider that the current guidelines, the conventional guidelines, are generally from the 1960s and 1970s. There's nobody updating them. Everybody recognizes that there's a problem, but it's impossible to do the type of traditional soil test calibration work that that scientists might want to do. Because to do soil test calibration work, you need to work with a specific crop and multiple soil nutrient levels, different rates of fertilizer, And you need to do that on all the soil types in which that crop is grown. Now you think about turfgrass. Turfgrass is one crop, but it's also different species. So we have perennial ryegrass and fine fescue and creeping bentgrass and brown top bentgrass and poa annua and kikuyu grass and seashore paspalum and manila grass and Japanese long grass. So many different types of grass. Tropical carpet grass, tall fescue. The list goes on and on. Let's say there's from 10 to 20 major common turf grasses in use around the world. Now think about doing a calibration study for each one of those grasses in every soil type in which it's grown. And we could collapse some of those soil types that are similar into groups. But even so, we now are, even if we simplify that quite a bit, we would have to have multiple soil types and all those different grasses. Then we need to look at all the different climates in which they could grow. So we could collapse that a little bit, but you can see there's a lot of climates around the world. And then we need to apply different fertilizer rates. And we need to do that multiple times. You can't just do that once. You'd have to either do that at multiple sites or over multiple years in order to check that it's something consistent. And then you've got the whole problem of, do we measure the yield? Because we're not really trying to get optimum yield. How would we measure our response variable? Well, for turfgrass, usually we measure the quality. And that's what we did with MLSN in a roundabout way. We assessed it by quality, not by yield. But the type of traditional calibration studies that one would need to do in order to update these guidelines, in order to have some type of modern recommendation doing things the conventional way, it is extremely unfeasible. It's impossible. It will never happen because it costs too much money and there's too many combinations. There's just no way to do those types of experiments. So we need something else. And that's why working with Wendy Galernter and Larry Stoll from Pace Turf, 10 years ago, we came up with MLSN. With MLSN, we focus very much on producing a surface. We look at the type of grass that we're growing and how we want it to perform, and we want to make sure that it's supplied with enough nutrients. We want to make sure that we make a fertilizer recommendation to supply enough nutrients to produce that surface. We are not trying to hit some fantasy target level in the soil. We're not trying to hit some optimum level in the soil. We're trying to make sure that the grass is supplied with enough nutrients. That's one thing we're doing with MLSN. And I think of the quantities in this way. We want to ensure that the grass is supplied with all the nutrients it can use. This quantity is the minimum amount to supply. I don't ever want the grass to not have access to all the nutrients it can use, except for nitrogen. I want to restrict the nitrogen, but I never want the grass to be restricted for phosphorus, potassium, calcium, magnesium, and so on. This is the minimum amount to supply. This is for professionally managed turf. Now, it's interesting that I use the phrase here, all the nutrients it can use. And if we think about the maximum amount to supply, it's the same thing, because adding more nutrients than the grass can use or than the soil can hold is a waste. Adding enough to ensure that the grass is supplied with all the nutrients it can use also turns out to be the maximum amount to supply. Because when you add fertilizer, you do not simultaneously increase the soil's ability to hold it. And when you add fertilizer, unless you're adding nitrogen, you're not increasing the grass's ability to take it up. The implication of this is that we can simplify the minimum and the maximum amount to be just the right amount, because it turns out they're the same thing. We want to supply the grass with all it can use. If we supply less than that, there may be a deficiency. If we supply more than that, it's a waste because the soil can't hold it and the grass can't take it up. I recently talked with Jackie Guevara, and I'll put a link to that conversation right up here. We recorded that in a ATC office hours. Jackie and I talked about her master's project that she did at Michigan State University. And what she studied was MLSN recommendations versus SLAN, conventional method recommendations, for phosphorus and for potassium on a bentgrass surface and on a bent POA surface over a 2-year period. For potassium, the SLAN recommendations were 300 to 400% what the MLSN recommendations were. And so she applied 3 to 4 times as much. I think it was exactly 3.78 times as much if you average over year 1 and year 2 of the experiment. The result was the grass quality was the same. There was no benefit to adding all that extra potassium. She also did soil testing at the start of the experiment and at the end of the season. All that extra potassium, it didn't increase the soil amount, it was just gone. So the MLSN treatment and the SLAN treatment, the conventional method, the historical method, the not modern method, applied 3.78 times as much potassium, 3.78 times more potassium than the modern method. But rather than increasing the soil levels, it just leached away. It was gone. And that's why I encourage turfgrass managers today not to worry about trying to hit optimum levels in the soil. They don't exist. And even if they did, it's impossible to have sand root zones hold some of those optimum levels, or these hypothetical, quote unquote, optimum levels. What I encourage you to think about instead is supplying the grass with just what it requires, the right amount of nutrients in order to produce a surface. We can do that with MLSN by looking at 3 numbers. We look at the expected plant use for the recommendation time period. The recommendation time period is the time duration over which we're going to make the fertilizer recommendation, whether that's 1 week or 1 month or 1 year. The second number we look at is the MLSN minimum value. That is a reserve amount in the soil that we want to keep untouched. And the third number is the soil test result right now. By expressing these 3 numbers in the same units, which the units I like to use are mass of element per area I think that's the unit. The mass per area of soil. So if you're American, you'll probably think of this in pounds per 1,000 square feet. I like to use grams per square meter. Other countries might use kilograms per hectare. So we'll take the soil test results, which are in on a parts per million basis generally, and we can convert that into a mass per area basis. So we talk about it all in units that are related to fertilizer recommendations. We have those 3 numbers, and then we can do a little bit of adding and subtracting, and from that we get the fertilizer requirement. How this works is we've got A, which is a site-specific estimate of plant use for an upcoming period over which we're making that fertilizer recommendation. We've got the value B, which is the MLSN guideline, the minimum amount that we want to make sure remains untouched in the soil. C is the soil test result. If we take A plus B, that's the amount we need. We subtract the amount that we have, that's C. A plus B minus C gives us Q, the fertilizer requirement. This is something that you look at these numbers A, B, C, and Q, and I'll try to explain a little bit intuitively what they are. A is what the grass uses. So we can actually think that we can just supply that. We could just drop B and C out of the equation and just say A equals Q. And I recommend this for situations where people don't believe the nutrients in the soil will be available. If they think they have a complicated chemical problem or saline irrigation water and they're doing a lot of leaching, just any type of case where the soil test results might be inaccurate or not trustworthy, or maybe you don't do soil testing at all. Maybe you don't want to, or you don't have access to a lab to easily do that, or don't have a budget to do soil testing. You can just drop the B and the C right out of this equation. It simplifies to A equals Q. The quantity of the element used by the grass is the amount to supply as fertilizer. That makes sense, right? And then you might think, well, some of the nutrients I apply might not be plant available. Some of it might get held by the soil or leached away or something. Well, in that case, take A times 1.1 or A times 1.2. Increase the value by 10 or 20%. Add a little bit more than the grass can use. That's still a reasonable amount. And A equals Q in that way happens to be what precision fertilization is, which is the method developed by Tom Erickson and now recommended and explained so well and promoted by the Scandinavian Turfgrass and Environmental Research Foundation, STURF, in the Scandinavian countries. That is a method that guarantees that no matter what soil you're growing in, no matter what type of climate you're growing in, no matter what type of surface you're trying to produce, you will be supplying the grass with 100% of what it can use. A equals Q. You don't even need MLSN. And it turns out if you do that, you'll supply less fertilizer than is commonly applied, because what happens in the turfgrass industry around the world is an attempt to hit target levels in the soil. So people end up applying more P and K than is otherwise necessary. It's certainly more than the quantity A. And they're doing that to try to hit unreasonable, unreachable levels in the soil. But the problem that we might have with A equals Q, the precision fertilization approach, which completely ignores the soil, the problem that we have is the soil often can supply a substantial amount of nutrients. The soil sometimes can supply all the nutrients the grass can use. So in that case, it's terribly inefficient to be supplying nutrients to the turf when the soil could already supply all those nutrients. Now, the way that we can account for that is to add in B minus C. B is the value that we developed using MLSN, the MLSN research project. That's an amount that in that equation, you notice that it is added to the amount that the grass uses. So that means it's an amount that we want to make sure is present. And then we subtract the amount that we actually have. The amount that we actually have is what we measure on the soil test. So if we want to account for what's in the soil and what the soil can supply, we add in that B minus C portion of the equation. And now we get A plus B minus C equals Q. And now we have the fertilizer recommendation using a modern method of MLSN. That MLSN value is not a target value. It's not a number that we're trying to hit in the soil. All it is a minimum value that we want to remain unused by the grass, and it fits into that equation so that we can make a fertilizer recommendation based on the amount the grass uses, this amount that we want to keep untouched in the soil, and then the amount that we actually have in the soil. Now I move on to the why MLSN works section, which has a little bit of overlap with the how MLSN works section, but I think for some reason this is not the way everybody's traditionally thought about this. In fact, when I was working with Larry to develop MLSN, I was spending some time beating my head against a wall trying to figure out how we could do this, because this is a very unconventional way to make a fertilizer recommendation. The way that we're taught to do it is very much agriculture based, and it's based on those types of calibration studies that I described earlier, which takes a crop like corn and it grows that corn in different soil types with different levels of nutrients, and then the experiment in those different soil types, all growing corn, will have different phosphorus rates applied, for example. And another set of experiments will have different potassium rates applied. And then one checks what the soil test level was, one checks what the soil test level was in all the different soil types, one checks the quantity of potassium applied, the quantity of phosphorus applied, and one checks the yield of the corn. From that, those calibration studies then say, here's how much should be applied to give the maximum economic yield. Now with turfgrass, we're looking at quality for one. So the main thing that we want to do is not hit some optimum level or have a maximum yield. We want to prevent deficiency. With turfgrass, we're really concerned about the low end, because we can have excellent turfgrass conditions across a wide range of soil nutrient levels. If you've got soil that has enough potassium and then you add a little bit more potassium, it doesn't make the turf worse. It doesn't make the turf better. The turf continues at that same high quality. But if you have turf that doesn't have enough potassium and then you take a little bit more away from the soil, now we've got a deficiency. Now we've got a problem. So everything for turf, it happens at the low end. That's what we're really concerned about. And with MLSN, we looked specifically at the low end. We took a large set of soil data from good performing turf. I took a few photos and put them on this slide. These photos are all from sites that had data included in the MLSN analysis. This is all professionally managed turf. I have a high confidence that professionally managed turf is good. It's at a good level. Sometimes turfgrass academics, professors, get very concerned about what good turf is. And that's a very important question. In the case of MLSN, we didn't go look at it or rate it ourselves. We relied on the turfgrass managers. And I am quite confident that when turfgrass managers are managing turf for a living, that the turf is good unless they flag it otherwise. Okay? So we excluded all the samples that were from problem areas. We excluded all the samples that were from research projects. We excluded all the samples that were top dressing sand checks or those sorts of things. We only included the samples that were from good performing turf, and that good performing turf is because it was from a professionally managed turfgrass site. And I use these pictures to show this is the level of good performing turf that we're talking about. Then we, I'm not going to show all these slides. I'm not going to work through all the charts. I'm not going to show all the charts about how we calculate this, but I show a few of them to show an overview of what we did. Here are 16,163 samples from the MLSN data set that show time on the y-axis, on the vertical axis, paste turf samples in orange, ATC samples in green. We put those together and we looked at how much potassium. We did this for every element. This is just potassium that I show the example for. So we took all those samples, and if we plot that as a histogram, well, let me point out one thing. I'll go back. Here we have 16,163 samples from good turf. Then we cut it. We took some away. Number one, we took away all the samples with a pH greater than 8.5 because I don't ever want to grow grass in soil that's greater than 8.5. So I'm always going to recommend to bring the pH down. We also threw away all the samples with a pH less than 5.5 because I am generally going to recommend to increase the pH to 5.5. We don't really want to grow grass below that. And then we made a big assumption that I know everybody will agree with. Well, I expect most people will agree with. And that big assumption we made was that if there's a lot of potassium in the soil, there's plenty of potassium available to the plant. Basically, we made the assumption that if there's a lot of a nutrient in the soil, the plant has access to a lot of nutrients. High nutrient soils, the assumption we made is that high nutrient soils are high nutrient soils. And so we got rid of those. So we made a cut also at a cation exchange capacity of 60 millimoles of charge per kilogram, or in the more common units that a lot of people use, 6 centimoles of charge per kilogram, or that would be 6 milliequivalents per 100 grams. So after we made those cuts at pH 5.5, 8.5, and CEC, we have this. We have 3,683 samples from good turf. And then we calculated something called the cumulative distribution function. And that is that curved green line that starts at 0 and goes up to 100%. And we then found the 10% mark on that line, the 10% point on that cumulative distribution function. If we find the 10% mark, what that means is 10% of the samples in the data set are less than that value. You see, if you look, for example, at that curved line, look at where it's at 75%. Look at the y-axis on the right side, 75%, and then move left across the chart and see where that intersects that curved green line. It's right at about 100 parts per million. It's at a level of potassium soil test of about 100 parts per million. What that means is 75% of the samples in the MLSN dataset after we made those cuts are less than 100 parts per million. So we picked the 10% level to say, even though these have good performing turf, we need to pick some threshold value that we think will be safe. And we picked that 10% value. So that's where the MLSN numbers come from. So we threw away the bottom 10% so that we have a safety margin or a buffer, even though we know good turf can be produced below those levels. I use as an example how this works and why it works the soil test potassium from Keia Golf Club in Fukuoka, Japan. This is soil test potassium on greens in those charts on the top right. We have soil test potassium and the potassium applied as fertilizer. Soil test potassium since 2013 has ranged from 60 down to about 40. just above the MLSN minimum of 37 parts per million, and the potassium fertilizer has ranged from about 2 grams per square meter, which is 0.4 pounds per 1,000 square feet, up to almost 8 grams per square meter, which is about 1.6 pounds of potassium per 1,000 square feet per year. That's how the fertilizer recommendations change and the fertilizer amounts applied change, and we just keep the soil test level from dropping below the MLSN minimum. For phosphorus, it's a little bit more interesting because the phosphorus at Kea Golf Club, when we first did that testing in 2013, which was the year after MLSN was introduced, the soil test phosphorus was almost 200 parts per million. And it has now dropped down to close to 50 parts per million with only 2 phosphorus applications over the past 9 years. Because when the phosphorus is above the MLSN minimum, that means the B minus C value is a negative number. It means the C value is the amount in the soil, B is the amount we need to make sure we have in the soil with a 10% safety margin. If that's a negative number, B minus C, that means that the soil has more phosphorus than the grass, or than we need to keep as reserve in the soil. So typically then we would end up not recommending it as fertilizer. You might wonder, why was phosphorus applied twice? Well, it was in some granular products that were applied to the greens, and it happened to be in the granular product that had the type of nitrogen source and the nitrogen release characteristics that the golf course superintendent, Andrew McDaniel, wanted to use at those times. The result of this is that over a 9-year period, the potassium application rate was 45 grams per square meter, which is an average of 5 grams per year, or an average of 1 pound of potassium per 1,000 square feet per year. And the phosphorus amount has been 1.1 grams per square meter over 9 years, which is an average of about 0.12 grams, 0.13 grams, something like that, per square meter per year. A very low amount of phosphorus. These are both considerably less than average, and yet the turf quality is fine. This isn't about minimizing fertilizer use. It's about getting the optimum quality and achieving that goal of producing the surface and supplying the grass with just the right amount. Just the right amount is simultaneously the minimum amount to apply and the maximum amount to apply, and it is the amount that the grass will use, all the nutrients the grass will use. All those equations, everything with MLSN was designed and calculated in a way to make sure that the grass won't have a nutrient deficiency and that the grass will be supplied with all the nutrients that it can use. That is something that there's plenty more information at asianturfgrass.com and at paceturf.org. If you have any questions about that, please check out those websites or check out some of my other videos, because I've also explained this in a few other ways, and some of those might also make sense to you. Thanks so much for watching.